continuing with 9.3, we're going to talk about the next test, which is the p-series test. P-series is a type of series that follow this pattern. The summation of 1 over n to the p, and if this is the case, it will be 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and p is a positive constant. For p is equal to 1, the series will just be 1 over n to the first power, and this is called a harmonic series, and harmonic series is a divergent series, and this goes back to looking if we were to find the improper integral of 1 over x as the limit goes from 1 to infinity. We're going to see that this will diverge. This will end up being natural log of u, and if we plug in upper and lower bound, this will go to infinity. So because the integral of 1 over x diverges, then so will this harmonic series of 1 over n to the first power. All right, so here's the rule for p-series. P-series will converge if p is greater than 1, and will diverge if p is less than 1. Less than or equal to 1. Okay, but I split this up into another condition where it will diverge if p is equal to 1. So technically, this b and c are the same condition, but I split this up because we have a special name for this p equals 1, and this is a harmonic series, and there are some special traits with this that we're going to see later on. So we could just combine b and c together and make it p is less than or equal to 1, but I just wanted to highlight this p equals 1 does have some special properties that we're going to keep coming back to later on. Also, we have a special name for that called harmonic series. Okay, so basically, converges if p is greater than 1. Anything else, it'll diverge. Okay. If the p-series converges, we cannot find the sum. We can do partial sum, but it is not like it's not like the geometric test where we can easily find the sum using that formula. So we cannot find the sum easily, but we are able to find approximation always by using partial sums. And we'll talk about remainder or finding remainder later on as well. Okay. All right, so convergent and divergent p-series. For this first example, the summation of 1 over n root n. Again, we should always be checking the nth term for divergence test. Nth term test for divergence, and we see that the limit as n approaches infinity, this will go to 0, so it is going to be inconclusive. But we can turn this into a p-series by combining these n's together. This is n times n to the 1/2. We add exponents n to the 3/2, and this is in the form where n is in the denominator, and that p-value is that constant 3/2, and 3/2 is greater than 1. So therefore, by the p-series test, this series will converge. The sum will converge. Okay. Next one here, part B, n over root n. We actually can use the nth term test and see that this n is growing faster than root n, so we could technically say that this will just diverge. We don't have to go through p-series, but if we were to go through p-series, we could as well. We can take the square root of n and cancel out, subtract the exponents, make it n to the negative 1/2, and p is equals to negative 1/2, which is less than 1, and so our series will diverge. Okay. Next example, we can go through nth term test, and we see this will be inconclusive because n is growing at a faster rate than root n, so this will go to 0. The limit as n approaches infinity will go to 0. So inconclusive for nth term test, but we can do p-series test by subtracting exponents and canceling out, making this 1 over n to the 1/2. 1/2 is less than 1, so our series will diverge. All right, this next one looks complex, but this is this value in the numerator we can pull out as a coefficient, and the denominator is 1 over n to the 1.0001, and this is p-series, and with this p-series we see the p-value is greater than 1, and because it's greater than 1, our sum will converge. Summation of 1 over n squared, this is easy to spot. P is equal to 2, which is greater than 1, our series will converge. 1 over square root of n, that's n to the 1/2. 1/2 is less than 1, our series will diverge. 1 over n, p equals 1, so this is a special case here. Harmonic series will diverge. Remember, with p series, will only converge if p is greater than 1. If it is equal to 1 or if it is less than 1, then our sum will diverge. Okay, determine whether the following series converge or diverge. And in this case, we can't go through p series. We have this natural log of n that is making it difficult for us to combine. And if we do nth term test for divergence, we see that this will go to 0. So we're not going to be able to get a conclusive read on whether this is convergent or divergent. So what other tests is available to us? We have geometric series test, but this is not geometric series test form. What about the integral test? So with the integral test, we can try this. This is continuous for n is greater than 2. We know that this is positive, always positive, because we have n is greater than 2, and also always continuous. So we can go through, let's try the integral test. So we find the limit as b approaches infinity from 2 to b of 1 over x ln x. We have to go through u substitution. We let the u value be natural log of x. Derivative is 1 over x. Cross product, dx equals x du. We replace, actually I should have a dx over here. We replace the dx with x du. And once we do that, the x's cancel out. 1 over u is natural log. So natural log of x, evaluate between b and 2. So natural log of b, as b approaches infinity, this will go to infinity, minus a finite number will give us infinite, a value that is infinity. And we see that this integral will diverge, and because of that, by the integral test, our sum will diverge as well.